everyone. Boy, oh boy, you've been doing such good work. Mrs. Hanson here again, and we're picking up our lessons with section 5.3, learning about the patterns of chemical change. So I'm really looking at the top of page 4, just so you see where we're at in our notepad page. Types of chemical reactions. We will learn that there are 5, majority of chemical reactions fall into 5 general categories. Our text uses 6, and I'm going to cut that back to 5. Here's why. A combination, I would want you to know, decomposition, single replacement, double replacement, a larger umbrella I'm going to pull out called redox, and then an acid-base reaction, which comes up in chapter 9. We'll kind of seed it today in this lesson and come back to it and visit in chapter 9. So for your lessons, I would like to write down 5 general patterns of chemical change. We're going to go through these one pattern at a time. The first of the 5 I want you to write down is called a combination reaction. Some texts call it a synthesis. We're going to call it a combination. Notice the pattern of change says I take a reactant called A, and I combine it with the reactant called B, and I form a single product, AB. This single product makes this combination unique. From all of the other patterns of chemical change, combinations are the only pattern that makes just one thing on the right side of the arrow, a combination reaction. Notice we have an element A represented by a blue molecular atom, B represented in green, and I combine to make AB, and keeping the equation balanced, we can see that I have 4 atoms of A reacting with 4 atoms of B, giving us 4 compound AB. It is a balanced equation. We know it would need to be in the reduced form to be properly written. The opposite of a decomposition, the opposite of a combination is a decomposition, where we have compound AB breaking down into the elements A plus B. Decomposition is the only pattern that begins with a single reactant. AB breaks down into A plus B, a decomposition. Notice that these two are opposites of one another. To combine is a building process. To decompose breaks it back apart. Combination and decomposition. The third pattern is known as a single replacement. This is where we take an element and react it with a compound to produce a new element and a new compound. An element plus a compound where we form a new element and a new compound. Notice what happens here is that element A kicks out element B from the compound and steals its partner. A single exchange, a single displacement, single replacement, where the elements A and B swap places. And the fourth general category is known as a double replacement. And the double replacement, we have compound A plus B reacting with compound C, D, and we see those swap places. The 2 positive ions exchange places, forming a new compound, AD, and a new compound, CB. And remember how we always write positives first? So A goes to D, C goes to B. A compound reacting with a new compound, forming 2 new compounds. The 2 positives exchanged partners. Compound AB react with compound AD, A then combined with the compound D, and C combined with B to form 2 new compounds, a double replacement. And the combustion pattern, we said, well, this is where we take a hydrocarbon, combine it with oxygen, and form carbon dioxide and water. And it releases all kinds of heat and energy and light. This hydrocarbon is some sort of fuel that you're burning in a combustion pattern. The 5 general equations, general patterns of chemical change. Combinations produce a single product. A decomposition breaks it back down. We have a single replacement where an element reacts with a compound, and a double replacement where 2 compounds exchange partners. And the combustion, where we have a hydrocarbon fuel burning an oxygen to release carbon dioxide and water. Can you practice recognizing what a combination and what a decomposition is? Pause the video and just try out labeling. Are these combinations or are they decompositions? Are you ready to check? Okay, I hope you paused. In letter A, what I want to see is if the one substance is on the reactant side or is it on the product side. I can see that the one product on the right-hand side made this a combination pattern, that copper and sulfur combined to make a single product. What makes the decomposition unique is that you start with a single reactant. And when that happens, you break down into a simpler substance. And that's our trick for picking out a decomposition, is it has a single reactant. Letter C, I notice that I have a single product. And that means that this is known as a combination. Whoops, I needed a pen. What about letter D? Combination. Now letter D, this is a hydrocarbon, but it's not the pattern of combustion because there's no oxygen on the left-hand side. We need a hydrocarbon plus oxygen releasing carbon dioxide and water. But I do want you to notice that it has just a single reactant. And when it has just a single reactant, it's known as a decomposition. So we had combo, decomp, combo, decomp. Here's a nice visual to remind us about single replacements and double replacements. Single replacements. Here I have a single replacement. This girl leaves her guy for Joe. So here's Joe. And this is Mary. And this is Frank. Frank and Mary are a couple. But here comes Joe. You notice what Joe did? He displaced Frank. Frank, poor Frank, it says. A single displacement reaction. Now, here's where our Frank and Mary. And over here now is Josh and Sue. Joe, oh, they've labeled these guys all differently. Let me get this caught up. This is Joe. This is Mary. This is Josh. And this is Sue. All right. So now look what happens. Joe and Sue are now together. And Josh and Mary are now together. This is what we call a double exchange, double replacement, double displacement. The 2 positive ions simply exchange partners, a double replacement. Now with that cartoon in mind, let's classify these as singles or as doubles. Pause the video and label single or double replacement. Come back when you're ready to check. Please don't cheat yourself of the practice. Okay, so we're given balanced equation or just trying to recognize the pattern. So when I'm looking at element, let's just make them all different colors. Notice that that has 4 different characters. This is like saying compound AB reacts with compound CD. A went with D, C went with B. And so notice our color code, copper, is now with chloride. They have a new last name. Hydrogen is now with oxygen. They have a new last name. This is a double replacement. Two compounds have exchanged positive ions. Now the difference here, when I recognize the elements, I have a zinc, a hydrogen, and a chloride. I have an element plus a compound. Well, I can see the zinc and the chloride now hook, and what's left is the hydrogen by itself. Notice I only have three colors, if you will, in my equation. Zinc kicked out the hydrogen, so that was a single replacement. Again, how many different elements allows us to predict? Letter A, here's a magnesium reacting with a nickel and the last name nitrate. 3 characters. The nickel is now by itself. The magnesium is now hooked to the nitrate. We have 3 different ingredients. Magnesium displaced the nickel in a single replacement. In your next, you notice that there's 4 characters: a potassium, an iodide, a tin, and a nitrate. Those are the 4 characters involved in this reaction. So 4 characters means the 2 positives have simply exchanged places. Potassium went with nitrate, tin went with iodide. That is a double replacement. Identify the characters. There's potassium. It's hooked to cyanide. Here's a hydrogen. Here is a chloride. The 4 different characters in letter C. We can see that the potassium hooked to chloride, hydrogen went to cyanide in a double replacement. And the last one to check, we had a sodium, we had a aluminum, and then a sulfate, SO4, a sulfate. That's 3 different characters. The sodium displaced the aluminum and stole its last name, the sulfate. So this is a single replacement. Now, what if they're all mixed together? Can you try this one out? Work ahead of me and come back. Tell me if they're combo, decomp, single, or double. All right. So here we're just looking to see what the pattern of chemical change is. Letter A, I have a single reactant. A single reactant means just one thing on the left-hand side. When that happens, you know to classify that as a decomposition. Now, in letter B, it looks like I have 3 characters. I have a magnesium, I have a zinc, and I have a chloride. 3 different characters means an element plus a compound. Magnesium displaced the zinc, so now it's by itself. Magnesium stole the last name, magnesium chloride. Single replacement. Letter C, what did you find? Well, I find that I have just one and only one product. And that makes that unique to a combination reaction. And finally, you would notice the K, the NO3, the H, and the Br as 4 different characters. The potassium went to the bromide, the hydrogen went to the nitrate, and you called that a double replacement reaction. Recognizing the patterns of change. Now we have a little more of a challenge here, is kind of figuring out what's missing in these balanced equations. All right, so we're told the pattern. We have to be detectives and figure out what's missing in the box. A combination reaction combines to make a single product. When carbon and oxygen combine to make a molecule, it will form carbon dioxide, a combination that simply comes out as a balanced equation already. Now, letter B is a decomp, MgCO3. When it decomposes, I've accounted for the magnesium and one of the 3 oxygens. What's missing? Well, and I ask myself, what's missing? I have a carbon and 2 oxygens that are missing. That's carbon dioxide. So it's like a subtraction problem. Think of this as an addition problem, and think of this as a subtraction problem. MgCO3, when I take out MgO, what's missing? Well, that's a carbon and 2 of the oxygens. That's carbon dioxide. When I'm adding carbon to oxygen, put them together. It's an addition problem. Decomps are subtraction problems. How about a single replacement? All right, so let's figure. I've got silver and then something. And on this side, I have lithium and silver carbonate. Now, silver is a +1, carbonate's a -2. That's why we crisscrossed and got Ag2CO3. Well, what's missing over here? I have to have the element lithium because it's now by itself, and its original last name was carbonate. The name of the compound is lithium carbonate. And remember, when I write formulas, I have to consider charges. So remember, we got to bring that around and down. Li2CO3. And the pattern of change would simply show silver kicking out lithium and stealing its last name. Silver carbonate forms and the element lithium. One more, a double replacement. We're given sodium carbonate. Now sodium is a +1, carbonate a -2. Use your polyatomic chart if you still don't have those memorized. Your carbonate, CO3 -2. And it's going to have barium, bromide, BaBr2. Now the double replacement says the sodium goes to bromide, barium goes to carbonate. When you write your formulas, remember to consider charges. When you are hooking to a new negative or a new positive, you have to balance that electrically. So the first, when sodium, who comes as a +1, combines with a bromide, who comes with a Br, it's just simply NaBr. You do not bring the subscripts with. But I find the new subscripts based on the charge. Barium, who comes as a +2, will combine with carbonate, who comes as a -2, so that's also electrically balanced. We'll need a coefficient in front of here to balance the number of NAs and BRs. So to finish that, you ended up having 2 units of sodium bromide and 1 unit of barium carbonate. And that created a balanced chemical equation. A double replacement. Exchange the 2 positive ions and check the charges as you do so. You've got an opportunity to practice. Classify, 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 and then down here you're going to fill out the remaining boxes. You have a job to do. I'll give you some time to do it. Pause the video, work ahead of me, solve each of these, and come back only when you have an answer to check. Working on page 5. All right, you must be back, so you've got these answered. You've paused and are ready to check. We have a single reactant in letter A. That's our clue that this is a decomposition. We broke it down to a simpler product. They're even showing you the bond that broke. In letter B, we can see an element, fluorine. We can see a compound, sodium bromide. And when I see that pattern of chemical change, the fluorine displaced the bromine and stole its partner. An element kicked out another element to form a new compound. So a single replacement. Letter C, what I notice is only one product. And that's our clue that that was a combination reaction. And how about this guy, letter D? We have 4 different characters. Did you notice? A hydrogen. We have nitrate. We have a potassium. And we have an OH. And remember, this is my trick. I really like you to just think about HOH for water, because now I can clearly see that I have a hydrogen and I still have a hydroxide as separate. So 4 different characters. The hydrogen went to hydroxide, the K went to NO3. This hydroxide is 1 unit, 1 polyatomic ion. So that was your double replacement. 44, do you see aluminum kicking out the hydrogen and stealing its partner, aluminum chloride and hydrogen gas? Do you notice in B how we had just 1 reactant, making that your decomposition? Hydrogen went to hydroxide, sodium went to sulfate. There's your double replacement. Think of water as HOH, hydrogen hydroxide. And here, with our next example, oops, I touched something. This has a single product. That's what we noticed as our combination pattern. Let's fill in what's needed. In a combination reaction, the compound that formed was sodium chloride, and you can see based on charge why sodium and chloride are combined in a 1-to-1 ratio. Na is a +1, chloride is a -1. And yet the elemental form of chlorine comes as a diatomic molecule. I can't just write Cl in that box because chlorine doesn't work that way. It comes as a diatomic. So then you had to balance as well. 2 NAs plus Cl2 made 2 NaCls. Excellent. Decomposition. Well, that one compound is going to decompose into its elements. The elemental form of nitrogen is N2. The elemental form of iodine is I2. Horses need oats for clear brown eyes. Those both are diatomics. So now we'll need to balance. We'll balance with a 2 in front of Ni, 3. That gets the N's working. Oh, and then I'll need a 3 in front of the I2's. That gets me 6 on both sides. Elemental form of chlorine with potassium iodide. Chlorine displaces the iodine. Iodine, remember, is one of the lucky 7, I2. Positive ions are written first, negative ions written last. KCl. Based on charge, you know that that is a K plus, a Cl negative. So that only goes as a 1-to-1 ratio to balance charges. And now we can balance by making 2's in front of each compound. 1 chlorine plus 2 units of Ki form 1 iodine and 2 units of KCl. And the double replacement, potassium hydroxide plus hydrogen iodide. K goes to I, H goes to OH. So the first product would be potassium iodide, and H goes to OH. You can write water as HOH. And know if you were typing that in to your homework site, that would go in as H2O. But I like to balance the equation HOH. All right, I'm going to keep going. Magnesium nitride formed. Notice this is a combination, so I'm building a compound from its elements. The elemental form of magnesium is just Mg. So then I just need to balance by placing a 3 in front of it. 3 Mg's combines with elemental form of nitrogen, and notice based on charge, magnesium is a +2, nitride a -3, so we crisscrossed and found our formula, and we balanced the equation. Letter B, when sulfur trioxide decomposed, the elemental form of oxygen is what's missing, and it comes as O2. not just O. So then I have to work to balance 2 S's, 2 S's, 6 O's, and 4 plus 2 is 6 O's. Are you getting good at these? Copper must be a +2, bromide a -1. When silver kicks out copper, the elemental form of copper is Cu. The compound is silver, who's a +1, bromide, who's a -1, just AgBr, right? Do not bring subscripts. Find the new subscripts when you are balancing by charge. So I have a copper, Cu, plus AgBr, silver bromide. I'll need to balance 2 groups of Ag plus 1 group of copper 2 bromide yields a copper and 2 silver bromides. And we had one more, a double replacement reaction. Sodium's a +1, hydroxide a -1, H is a +1, bromide a -1. Oh my gosh, these are easy, all +1 -1s. So here we'll have sodium bromide, also a +1 -1, so it's electrically neutral. And then in H, who's a plus, OH is a minus, and so that balances as water. And a double exchange, sodium bromide and hydrogen hydroxide, commonly called water. That takes practice, my friends. Keep going. If you can work more and more and more problems, recognizing the patterns, and especially this skill requires practice, filling in what's missing and then going back to balance. Don't cheat yourself of the opportunity and think that you're proficient until you've worked enough problems. All right, that's my... Looking at a balanced chemical equation in terms of moles, letting us read a recipe card. So a balanced chemical equation tells us how many moles of each reactant combine and the number of moles of each product that form. The moles in a chemical calculation. What I just wanted to share is what coefficients truly mean. When I see 1 in front of a nitrogen molecule, we can read that as one molecular compound, one molecule of nitrogen, or an entire mole's worth of nitrogen molecules. They combine with 1 molecule of oxygen to form 2 molecules of NO. Coefficients stand for individual molecules, or it can stand for a whole mole's worth of molecules, and that's a much more practical thing. So we use these mole ratios as conversion factors to convert from 1 mole of a compound into the other, where the coefficients themselves become conversion factors. You look at a balanced equation as a recipe card. If we see that our balanced equation gives us 1 molecule of nitrogen, 1 mole of nitrogen, plus 1 mole of oxygen to form 2 moles of NO. What are those relationships? I could see that for every 1 mole of nitrogen, 1 mole of oxygen is required. I could see for every 1 mole of nitrogen, we produce 2 moles of NO. And I could also compare an oxygen to the product as well. All of these different mole ratios that are allowing us to convert from one unit to another from a balanced equation. I want you to consider the mole map that we were just practicing with the mole as the central calculation. If I'm weighing, I head into the mole using molar mass. If I'm counting, I head into the mole using Avogadro's number. All road leads into the mole. The same is true for our stoichiometry roadmap. Stoichiometry is the quantitative study of chemical reactions. Quantitative study. And that's what this is, the chemistry stoichiometry roadmap, where the road leads into the moles. This is our mole ratio. The heart of all of our problems, the mole ratio, are want over given stoichiometric ratio. Now notice, I can count, I can weigh, or I can take a volume. The three ways that we measure matter. We count it, we weigh it, or we take a volume. All roads lead into the mole, just like down here. We know to use Avogadro's number if I'm heading into the mole from counting. I know to use molar mass if I'm heading into the mole from the scale. And when we get to the gas laws, we'll learn the molar volume. If I'm given a volume, we can use our molar volume to convert to the mole. Just like molar mass, we have molar volume when we get there. When we're heading back out of the mole, we know to multiply. Multiply by Avogadro to get to particles. Multiply by molar mass to get to grams. Our 3 steps to stoichiometry: we divide, we ratio, we multiply. Those 3 steps allows us to convert between any ratios from a balanced chemical equation. As usual, it makes more sense if we dive in and just start doing some examples. When we look at a balanced equation, such as carbon monoxide, a poisonous gas that combines with hemoglobin in the blood, it reduces the amount of oxygen that can be delivered to tissues. So that's why you should never run your car in your garage with the door down. There's plenty of oxygen in the room, but the hemoglobin cannot combine to the oxygen because it has a higher affinity for carbon monoxide. When ethane, C2H6, is burned in the presence of oxygen, O2, the balanced equation is shown to us with 2 moles of C2H2 reacting with 5 moles of oxygen in the presence of heat. Remember, the triangle over the arrow means heat. We get 4 moles of carbon monoxide forming and 6 moles of water formed. Using this balanced equation, this 2 to 5 to 4 to 6, how many moles of CO that's what we want to know, are produced from 3.5 moles of ethane? That's our given. See what we're doing on our mole map? Given a mole, we want to calculate a mole. Now we call these a mole-mole problem. Pretty snappy, right? A mole-mole. Given a mole, calculate a mole. And the coefficients, the coefficients serve as our conversion factor, the heart of our stoichiometry roadmap, the want over given coefficient ratio, since coefficients stand for moles. We use the coefficients as a conversion factor. Now, since I'm at the mole, I don't need the first step. I wasn't given grams or particles or volume, and I only want to go as far as the mole, so I don't need the third step. It's just the heart of the problem, the want over given. So we're not needing the first step or the third step in our 3-step problem because we're not asked to go out that far. Given a mole, calculate a mole. It's a 1-step heart of the problem stoichiometry. Start by writing what was given. We were given 3.5 moles of C2H6. We need a conversion factor. The heart of our problem, our want over given mole ratio. And remember what we wanted to solve for? We wanted moles of CO. I'd like to know how many moles of carbon monoxide form if given 3.5 moles of the original C2H6. We want to know CO. Its coefficient is 4. We were given C2H6. Its coefficient is 2. the coefficients become the conversion factor. In a stoichiometry mole-mole problem, we use the balanced chemical equation to find the coefficients of what we want over given. So on your calculator, we would solve this by saying 3.5 times 4 over 2, and we get 7. 7 moles of CO will form. Hey, we just did our first mole-mole problem. Let's try another. Here's an example. Whoops, I have to flip our notepad page. Where the recipe gives us 1 mole of nitrogen to react with 1 mole of molecular oxygen, and it forms in the presence of heat 2 moles of NO. Coefficients stand for moles. These are mole-mole problems. Given a mole, calculate a mole. And in order to do that, we're right smack in the heart of our stoichiometry roadmap. We ratio. We use our coefficients of want over given. Given a mole, calculate a mole. These are mole-mole problems. How many moles of NO are formed if 3.3 moles of N2 were to react? Right, say, I know the perfect ratio is 1 to 2 from our balanced equation. What if we change one of them? What did the others do to keep the equation balanced? Start by writing the number you were given. We were given 3.3 moles of N2. What is it that we want to solve? And what is it that we were given? We're in the heart of our problem, the want over given stoichiometric ratio, mole ratio, where the coefficients are used as conversion factors. We want to know NO. Its coefficient is a 2. We were given moles of nitrogen. Its coefficient is a 1. So our mole ratio is 2 over 1. 3.3 times 2 over 1, and that's 6.6 moles of NO. So let's look at letter B. This time we're starting with 0.5 moles of molecular oxygen. What would the conversion factor be now to get us out to NO? We want over given. We want to know moles of NO. Its coefficient is a 2. This time we're starting at the oxygen, but it also had a coefficient of a 1. 0.5 times 2 is 2.5. And we have one more I'm going to put down here. If I have 1.2 moles of molecular nitrogen, this is my given. And I want to know oxygen. So just kind of keeping tabs. This time we have a new target. I want to know oxygen from nitrogen. So I go into the balanced equation and I find that both of those have coefficients of 1. So that calculation gives me the exact same answer back. For every 1.2 moles of nitrogen, you would also require 1.2 moles of nitrogen, of oxygen. Both of them are the same number. That was easy enough. Here's an equation where we start with 3 moles of molecular oxygen, and in the presence of sunlight, it converts to ozone, and ozone is O3. In the upper atmosphere, high energy radiation from the sun converts oxygen into ozone. Using this balanced equation, let's calculate how many grams of ozone are formed from 9 moles of oxygen. Now look at your stoichiometry roadmap. You have one of these in your notepad. You're going to be provided one of these in your test-taking tool page. Where are we given? We're at the unit mole, so we're right here. We're at 9 moles of oxygen. What do we want to know? We want to know grams of ozone. So what kind of steps will be involved now? I know that the heart of my stoichiometry roadmap is my want over given coefficient ratio. But I need to go one step further to get out to the grams of ozone. So we're going to need to, remember the first step is always divide. If I need to head into the mole, I divide. I don't here because I'm already at the mole, so I'm not needing step 1. But I will always ratio. That's always a given in the heart of a stoichiometry problem. But I will need a step 3 that will multiply to head out to the grams. So let's think about that. Given 9 moles of oxygen, that's me standing right here, I want to convert that to moles of ozone. And that's our want over given ratio. That's the heart of our problem. What is it that we want? What is it that we started the problem? What we were given? And remember, these are coefficients that are a conversion factor. We want to know ozone. Ozone had a coefficient of 2. We started from oxygen. Oxygen had a coefficient of 3. That first conversion factor ended from moles of given, and now I'm standing right here, moles of want. One more step to get to grams. And notice that? That's the molar mass of what we want. We want to know grams of O3. So the molar mass of O3 is 48. 16 times 3 is 48 grams of ozone in every 1 mole. So remember the mole map. To go from moles out to grams, that conversion factor is called molar mass. So we start with our 9 moles of oxygen. We multiply by a coefficient ratio of want over given, 2 over 3. And we'll multiply by molar mass of 48. And my screen reads 288 grams of ozone were formed. For every 9 moles of oxygen, 288 grams of ozone form. You just did what would be called a mole mass problem. Given a mole, calculate a mass. We started here and ended here, a 2-step conversion problem. Let's keep another one going. This one talks about wine being produced by the fermentation of grapes. In fermentation, the carbohydrate glucose, C6H12O6, is converted into ethanol, that's drinking alcohol, and carbon dioxide according to the given balanced equation. For every 1 mole of glucose, 2 moles of ethanol form, and 2 moles of carbon dioxide form, a 1 to 2 to 2. How many grams of ethanol? Well, I'm going to just make a note. That's my target. That's what I want to know, is the mass of ethanol. They're produced from 5 moles of glucose. So I'm starting here. I'm given the moles of glucose. And what do we want? Oh, we want mass in grams. What do we have? We have a step where we need our conversion, our want over given, coefficient conversion factor. And then we'll need molar mass to convert out to the other grams. So we'll need a ratio, and then we'll need a multiply. Start by writing our unit, 5 moles of glucose. We need a coefficient ratio of want over given, the heart of our stoichiometry problem. We want to know ethanol. Its coefficient is a 2. We started with glucose. Its coefficient was 1. That brings us from moles of given to moles of want. So now here I'm standing at the moles of want. I have another step though. I got to get out to grams. And I literally trip over my conversion factor, which is molar mass. And see how nice they were? They gave that to us in the story problem. 46.07 grams is the molar mass of C2H6O for every 1 mole. So we start by our mole quantity of 5. We multiply by our mole ratio of 2 over 1. And we're going to multiply by the molar mass of 46.07. And my screen reads 460.7 grams of C2H6O. We ratioed, we multiplied to solve that stoichiometry problem. We were given a mole and asked to calculate a mass. We call those mole mass problems. Let's do another. Here's a balanced equation in which ethanol reacts with oxygen to form carbon dioxide and water. Our mole ratio for every 1 to 3 makes 2 to 3. Coefficients are moles. Letter A. How many grams of carbon dioxide, starting with 0.5 moles of ethanol? I really would encourage you to pause, process this information, give yourself think time, try these 3 problems, and only come back when ready to check your work. Please give yourself the practice. All right, here's the heart of our problem, the want over given coefficient ratio. Our heart of our problem, we want over given, where coefficients become the conversion factor. Letter A gave us 0.5 moles of ethanol, C2H6O. We want to know grams of carbon dioxide. I know that it will require 2 conversion factors, so I'm just going to get those ready so I can see my target. I want to get to grams of CO2. Given a mole, we want a gram. These are called mole mass problems. Step 1, we need a mole ratio to convert from what we want over given. The coefficient of what we want, carbon dioxide, is a 2. The coefficient of what we were given is a 1. So the mole ratio of 2 over 1 brings me from moles of given to moles of want. So now I'm standing right here. I need one more step, and that's to get out to grams. We know that converting from moles to grams requires the molar mass as your conversion unit. The molar mass of carbon and oxygen, that gives me 32 and 12, that's 44.01 grams. Let's hit that out and see what we find. 0.5 times 2 over 1 times 44.01 is 44.01 grams. I'm embarrassed I hit that. It's the same number, 44.01 grams of carbon dioxide. Did you find that as well? Letter B gave us 2.4 moles of ethanol. But this time we wanted to know water. So with water's want over given ratio, we want to know water. Its coefficient is a 3. The coefficient of ethanol, still a 1. And in the next step, since we want to know water, we need to know its molar mass. So we have a new target this time. 2 H's added to an O 18.02 grams for the molar mass of water. 2.4 times 3 times the molar mass of 18.02, and my screen reads 129.7. Well, use 2 decimals, 0.74 grams of water. Maybe I should have just 1 decimal. And in letter C, 0.25 moles of ethanol, and we want to know grams of oxygen. So the oxygen coefficient is a 3. Coefficient of your ethanol is still 1. And this time, to get out to grams, we need the molar mass of molecular oxygen. So that's 32 grams of O2 in every 1 mole. 16 taken twice is 32. 0.25 times 3 times the molar mass of 32, and you found 24 grams of oxygen. How did you do? Oh, I hope these are getting easier. Ooh, here, I was just kind of reading ahead. We have ethylene reacting with water to form ethanol. These are all balanced with coefficients of 1. Ethanol, C2H6O. This has a molar mass of 46.07 grams per mole. I'm just kind of tabulating the information in the problem. It's synthesized by reacting ethylene. So ethylene is over here, 28.05 is the molar mass. So that's those numbers there. How many grams of ethanol are formed? That's what I want to know, is how many grams of this, that's my want, given 14 grams of ethylene. So that's my given. Ah, look at this fun. All right, what are we doing? You see where we're starting? We're way over here. We're at the mass of given. What do we want? We want to know a mass of the product. We're going to call these mass products. Mass problems. Given a mass, calculate a mass. We will need all 3 steps of stoichiometry. We need to divide to get into the mole. We'll then use the heart of our stoichiometry problem and do a want over given mole ratio. Then we'll need a step 3 to get back out to the grams of what we want. We'll divide, we'll ratio, we'll multiply. So let's start by writing what we're given. We had 14 grams, I'll do it right here, 14 grams of ethylene. That's C2H4. That's me standing right here, the mass of what is given. The first conversion factor needs molar mass to bring me from mass to moles. It's an old mole map problem. We know that 1 mole of C2H4 has a molar mass of 28.05 grams. That was given to me. Now I'm going to just get my 3 parentheses ready. I know it's a 3-step conversion. And I just want to get those 3 parentheses ready so you can see where we're trying to get. We want grams of ethanol, C2H6O. That's why we're given a mass. We want to calculate a mass. That's why these are referred to as mass problems. When you have to use the entire roadmap, you need 3 steps, 3 conversion factors. We divide by molar mass of given. We use the coefficient of want over given in your mole ratio. And then we multiply by the molar mass of the new compound that we want. Divide by given, ratio, multiply by want. All right, let's take a look. Step 1, we divided by 28 the molar mass of given. Now here's where we're standing. I need the mole ratio to pass through this step. I'm tripping over my conversion. What do we want? Well, we want ethanol. Its coefficient is a 1. We were given ethylene. Its coefficient was also a 1. So that's nice. A 1 over 1. Want over given mole ratio. So now I'm standing here. I have one more step to get out to the grams of what we want. And so that relies on the molar mass of where we're heading to, which is C2H6O. And its molar mass was given as 46.02 grams. We did it. 3 steps. Let's hit 14. We divide by the molar mass of given, 28.05. We ratio, which is 1 over 1. And then we multiply by molar mass of where we're heading, the 46.02 grams. This would yield 22.96897 if we round, about 23 grams of C2H6O. Given a mass, you calculate a mass by dividing, ratio, multiply. The 3 steps of stoichiometry. You divided, you ratioed, you multiplied. That brings us straight across the stoichiometry roadmap. Let's try another. I think the more we do, the better you get. I'll model one more and then ask you to try some on your own and come back. Here we have a balanced equation of salicylic acid reacting with acetic acid, forming aspirin and water. The coefficients are all 1s, 7, 8, 9, 9, 8. They are indeed. This is a balanced equation and the coefficients are all 1s. That's pretty nice. How many grams of aspirin form? How many grams of aspirin form if 10 grams of salicylic acid are started? Given a mass, calculate a mass. The 3 steps of stoichiometry. Start here and end here, knowing at the heart of your problem is your coefficient ratio of want over given. To move from mass to mole, the conversion factor is molar mass. We'll need the molar mass of C7H6O3. Let's go to work on that. Carbon 12.01 times 7 plus 1.01 times 6 for the oxygen plus 16 times 3 for the oxygen, so that's 138.13 grams. We're going to need a molar mass of aspirin as well, C9H8O4. Let me work on that. 12.01 times 9 for the carbon, plus 1.01 times 8 for the hydrogen, plus 16 times 4 on the oxygen. Oh, I didn't hit that right. It didn't look right. I hit plus, times 9. Plus 1.01 times 8 plus 16 times the 64. Yep, there it is. 180.17 grams per mole. All right, that's been out there before. We've used that one. That's why I knew it didn't sound right. Here's what we're starting with. 10 grams of salicylic acid. My first step is to move from grams to moles. I literally trip over my conversion factor. I know that 1 mole of C7H6O3 would weigh 138.13 grams. That's my conversion factor, the molar mass. We're now at the heart of our stoichiometry problem. What is it that we want from the given using coefficients as our conversion factors? Well, this was nice. We said 1 mole of aspirin is equivalent to saying 1 mole of salicylic acid. Couldn't be any nicer than a 1-to-1 mole ratio. That brought us from here to here. So I'm standing right here. I need one more step, and that's to come out to the grams. And remember, we need molar mass to convert from moles out to grams. We divide, we ratio, we multiply. In 1 mole of your aspirin, it would weigh 180.17 grams. Now we're ready. 10 divided by 138.13 times 1 over 1 times 180.17. And that answer is 13.04, and that's grams of aspirin. Now I've modeled many mass problems. I'd like you to try 3 more on your own and then just come back when ready. As a matter of fact, I think you have many to practice. I want you to turn this video off and I want you to finish page 10. That's where you are now. Finish up page 10. I want you to work all of page 11. And I want you to do up to page 12 where you see percent yield. Come back when you're ready to check. Are you ready to check? It probably took you a great deal of time in order to work through these, and I don't want you to cheat yourself. I want you to practice. So let's do some together. Letter A. I have 55.5 grams of salicylic acid. That's C7H6O3. I want to know grams of aspirin that will form. So it's very similar to the one we modeled. We know that 1 mole of C7H6O3, the salicylic acid, has a molar mass of 138.13 grams. That's my divide to head into the mole. All these coefficients are 1. It couldn't be any simpler. 1 mole of aspirin, I'll just write out its formula, which would be C9H8O4, forms from every 1 mole of C7H6O3. We want to know grams of aspirin, so we use its molar mass in this step. And when you hit, you divide, you ratioed, you multiplied. So I'm going to hit that, see if we got a common answer. 55.5 divided by 138.13 times 1 over 1 times 180.17. My screen says 72.39, and that would be grams of aspirin. I'm just trying to find out where my tiles went. There they are. Let's put letter B here. I don't know what's happening. All right, so letter B just simply says how many grams of acetic acid, that's the other reactant, are reacting with 55 grams of salicylic acid. So I'm going to need just quickly to C2H4O2. Let me find its molar mass. 12.01 times 2 plus 1.01 times 4 plus 32 from the oxygen. So there's its molar mass. So in letter B, we have the same starting point, don't we? 55.5 grams of salicylic acid. And so I know that my first step will be to convert using 138.13. It's still a 1 mole to 1 mole ratio. It's just that now we're going to acetic acid, C2H4O2. Step 3, I have to come down here and I'm going to use the molar mass I just solved for, 50.05 grams. "55.5 grams of salicylic acid. Divide by the molar mass of 138.13. The mole ratio is 1/1. We'll multiply by 50.05, the molar mass of acetic acid. And I found 20.15 grams of C2H4O2. This might be wrong. 12 times 2 is 24, plus 4 on the hydrogens, plus 32. Yeah, that's 60 grams. I just thought that looked wrong. Did you catch that? I'm so glad you helped me find that, because I knew that that wasn't the right answer, and I was able to pull out my mistake right away. This is 60 grams of acetic acid. I bet you're glad I fixed that so that you weren't going crazy. That's the correct answer all along. Let me now repair mine, and you can kind of compare without changing yours. "55.5 divided by 138.13 times 60, and that's the right answer, 24.1 grams of acetic acid. Good work. Takes a village. And in letter C, if I consider what letter C is asking, let me just bring that over. We want to figure out grams of water. And so the only thing that's going to change is that last step in which we compare 55.5 grams of our initial compound. We know that it will have the same first step over and over. We're starting with the same ingredient. We know that all the coefficients are 1s. Even the water had a coefficient of 1. But the only change now is the molar mass of water will be used in the last step. So all of that repeats, leading out to a new final answer, 55.5 divided by 138.13 times 18, the molar mass of water. And just to let you compare, 7.23 grams of water for part C. The next question used an equation of 1 nitrogen plus 1 oxygen yields 2 NOs. These are all mass problems. So you can see you're going straight across the stoichiometry roadmap. You divide, you ratio, you multiply. In letter A, we're given 10 grams of nitrogen. We use the molecular weight of nitrogen. 2 N's added together is 28 grams. We're at the heart of our stoichiometry problem. We want to know NO. Its coefficient is a 2. Starting from moles of nitrogen, its coefficient is a 1. Here now, 14 plus 16, that gives us a molar mass of 30 grams of NO in every 1 mole of NO. Did you get an answer? Let me catch up. 10 divided by 28 times 2/1 times 30. My answer reads 21.4, I'll say 0.4, that's good, grams of NO. We're going to start with 10 grams of oxygen in letter B. We use the molar mass of oxygen to convert it to a mole. 32 grams is the addition of 2 oxygens. We're in the heart of our stoichiometry problem, the want over given ratio. We want to know moles of NO. its coefficient is a 2. Starting with oxygen, whose coefficient is a 1. The nitrogen oxide molar mass was 28. No, it was 30, right up here. 30 grams. We divide, we ratio, we multiply. 10 over 32 times 2 times 30. See what we've done? Mass divided by molar mass. That's our step 1. We divided. Step 2, we ratioed. We want over given coefficient ratio. Step 3, we used the molar mass of what we want, and we did 3 conversions. Mass to mole, mole-mole ratio, mole out to gram. 3 steps of stoichiometry. 10 over 32 times 2 times 30. My screen reads 18.75 grams of NO. Letter C. This time you started with 10 grams of nitrogen. Nitrogen with its molar mass of 28. We want to know oxygen. Its coefficient is a 1, just like the mole of nitrogen, a 1-to-1 stoichiometric ratio. The molar mass of oxygen is used in the last step. So 10 over 28 times 32, 11.42 grams of oxygen. You did it.